If that is the case, then let us see in the original problem what is the situation, what kind of induced charges do we have. We have the expression for the potential for z greater than 0, positive z values. We have already found it, and we can calculate the surface charge density from the expression of the potential. Surface charge density sigma can be expressed as minus epsilon naught times the normal derivative of the potential on that surface. So, del V del N, just to recap, is the normal derivative, the gradient of V dot n cap for this surface. N cap is the unit vector pointing outward of the surface. So, if we now calculate sigma, that is minus epsilon naught del V del Z at Z equals 0, because Z is the direction normal to the plane that we have considered, the infinite metallic plane, infinite conducting plane. And we have the expression for the potential V. So, del V del Z can be given as 1 over 4 pi epsilon naught minus q z minus d over x square plus y square plus z minus d squared, this quantity power 3 over 2 plus q times z plus d over x squared plus y squared plus z plus d squared, this quantity over 3 over 2, this quantity power 3 over 2. Now, this is del V del Z, and we want to find del V del Z at Z equals 0. So, we will set 0 here for Z and 0 here for Z also at the numerator, and we will be left with. So, if we now calculate the expression for sigma, that is the surface charge distribution, that will be minus q d over twice pi x square plus y square plus d squared power 3 by 2. This will be the surface charge distribution, and as expected for plus q point charge in the z axis at a distance d along the z axis, we have an induced charge on the grounded metallic sheet of infinite extent of a negative sign, and this charge distribution, as you can see, if we have larger values of x and y, this induced charge, amount of the induced charge reduces, and on the other side of this metallic plane, conducting plane, the induced charge will go to the ground, because we have grounded the this conducting plane. So, by this charge distribution, induced charge distribution that we have found out, the metallic conducting plane will maintain itself at 0 potential. So, let us try to find out the total induced charge for this system. For total induced charge, we will have to integrate over the entire plane. So, the total charge will be integration over sigma dA And let's move to polar coordinate system now. The coordinates are r and phi. So we have to represent sigma in terms of that, which is just a function of r. It's symmetric in phi. So this will be minus q d over 2 pi r squared plus d squared over 3 over 2 x squared plus y squared equals r squared in case of 2 dimension. That is simple. So if we integrate it, we will get q over phi. The range of integration is 0 to 2 pi, over r it is 0 to infinity. We have the integrand minus q d over 2 pi r squared plus d squared power 3 over 2 r dr d phi. This is the surface element, and this turns out to be q d over r squared plus d squared square root of this quantity. The limits are from 0 to infinity, and that equals minus q. That means the amount of the total induced charge is the negative of the point charge amount that we have at a distance d above this plane, which is consistent with all our expectations.